have a lot of movement. Some people was yesterday and leave us today, so we have new persons today. So thank you everyone for coming here, for being interested in our conference. Thank you to my colleagues for helping us, because I don't know if I have the opportunity to thank them. So we will continue today with new lectures, and I invite now Professor Konstantinos Tsavdaridis, I'm sorry if I mistake your name, from University of Leeds, with an interesting subject. So, please, you will present better.
So I'm coming from the University of Leeds, and today I will present a topic on the combination of sustainability and seismic-resistant design of connections in steel buildings. I always start the presentation with a quote, and that particular one is just published a couple of months ago. It's from a project in the UK. And it says that the main message of that one is that although we've been talking for more than a decade now, it's nearly 2 decades, about sustainability, yet sustainability is not the priority of the design engineers. It is the priority of engineers in general, but not the ones who deliver the building, design actually the building. So the whole idea is about trying to marry these two concepts and see what we can do about it. So obviously, people working in sustainability talking about economy and circular economy, about the cost of the building, how they can reduce that. And the others, the engineers who deliver the building, talk about safety and seismic design. So these two concepts, sometimes they contradict themselves. So by this kind of research that we've been doing the last 10 or so years, from my previous university and then the last 7 years from the University of Leeds, we try to, as I said, to bring these two concepts all together. So talking about steel buildings and seismic-resistant design, obviously I couldn't miss the two catastrophic earthquakes at Northridge and Kobe 1995. The reason that I put actually this slide is not to show thousands of people that lost their lives predominantly, but to show that these earthquakes just happened in 1994 and 1995. So we're talking about like recent earthquakes. And as you can see from Wikipedia, thousands of people lost their lives. So there are a lot of buildings at the moment out there that they still use the same connections as those buildings. And that makes us think more about retrofitting rather than designing new buildings as seismic resistant, which is, there's a lot on that, but it's, I guess, easier. So the main lessons was that they avoid use much welding because they crack suddenly due to brittle failures. But more importantly and more interestingly, we found that there are problems in the vicinity of the welding as well, not just on the welding. So it was back then when people started talking a lot about the plastic hinges, the position of the plastic hinges, what's happening in the plastic hinges, columns or in the shear panel zone or in the beam, and what can we do in order to mobilize the shear stresses from the face of the column or near the support of the beam towards somewhere more inside by adding or reducing material. And by that it was the birth of the RBS connection, the reduced beam section connections as well. So the 4 different cuts at a specific location of the beam in order to fight the low inelasticity of the welding. So SAC venture was created and a lot of data was then transferred transferred to American design guidelines, and more recently, very, very recently, in fact, all this information is now getting into Eurocode 8, which is what we want to achieve also, a similar performance of buildings by using RPS connections. But talking about retrofitting, there are other ways that we retrofit buildings. I would say the other ways that we commonly use to retrofit buildings, and these are shortening span, adding beams, replacing with stronger members, etc. But all these methodologies, they have one thing in common. They increase the weight of the structure. So that is exactly against to what the sustainability says. So we're not thinking about whole life cost. We're increasing the maintenance cost of the structure. We're increasing the weight of the structure. We're definitely increasing the how many man hours we have to work on these structures to add all these little pieces and bits, all the components of the connections to make them stronger. At the same time, the last decade or so, again, it's around like 15 years, we're talking about performance-based design. So performance-based design is in fact designing bespoke buildings, okay, buildings for the needs of the particular building. But performance-based design is used predominantly by structural engineers. It's not used by anyone who's working on sustainability. So what I like thinking is more an optimization rather than a bespoke performance-based design, where we can bespoke design other things at the same time. So we can think about sustainability, but we can think about resilient structures, flexible structures, adaptable, safe, as what the seismic engineers do, but also lightweight structures. So to me, sustainability is actually this holistic optimization of your structure. Which some of us we do, but as we saw at the beginning of the first quote, is not the priority. So I was fortunate enough since 2005, 2006 to work in a group that we were working mainly on the design of perforated beams. So cellular beams, in fact, as they used to be called more when they have circular web openings. Has anybody worked on designed any perforated beam? Okay, just one person. You see, it's although the first perforated beam was designed in 1956, I think, in the US, yet not many people are using perforated beams. And there are lots of advantages. I just write down a few of them here. The main one is that, as you can see on the right-hand side here, you can, instead of having the services, so hydraulic pipes and electric wires passing under the beam, you can integrate that service zone within the depth of the beam, which means that you are minimizing or reducing, let's say, the structural depth, which means that you can gain more space, or you can have more floors in a given volume of the building. So service integration, number one thing, but having lighter beams, you can have longer spans. By having longer spans, we have fewer columns, fewer foundations, a lighter structure, so the impact of using perforated beams is huge, and it's towards sustainability. So that's why we kept on working on that. In 2017, the New Steel Construction magazine in the UK actually quoted that the last decade, the use of perforated beams in steel frames has been increased from 40 to 90%. We believe that that was from our impact. In fact, the three pictures that you see here, they are from Leeds. The one on the top, I just got it a couple of days ago from London. So there are all sorts of versions of different perforated beams, what we call the ones made by profile cutting process or cutouts, but they keep on using them a lot in the UK. I don't think that there's any sort of steel structure or composite structure that they don't have perforated beams. So back in 2006, we did a lot of tests, understanding the behavior, this complex behavior, as the design guidelines call it, of perforated beams with standard and non-standard web openings, looking at what's happening between the two web openings. Here, the web post, looking at the veer-and-till mechanism, so the shear mechanism, understanding all the different parameters and what is the impact of every parameter, and more importantly, designing these shear moment interaction curves where engineers can use them directly and get the capacity, find out the capacity of the perforated beams. So we contributed significantly to the Steel Construction Institute publication 355 in 2011, which is the main guidance that we use globally for the design of perforated beams with the large web openings, composite and non-composite. And more recently, we're taking all this information and we put it in the Eurocode 3. So in the new updates, perforated beams will be there. Now, I'm going to go slightly a little more in detail, but not too much. So there's no formula or anything like that. It's going to be just a few things to understand what it defines the behavior of perforated beams. So we mainly look at these four plastic hinges, these four nodes that we see, which is where the stress is concentrated. When we have openings like this hexagonal opening, the position of plastic hinges is always these corners. But we don't use hexagonal anymore because of some issues related to cracking, so we use the cellular web openings, which is the circular ones. The problem with these ones is that the position of the plastic hinges is highly asymmetric, and in fact it's changing while you're changing the position of the opening along the length of the beam, so different shear moment interaction on the center line of the opening. So we needed to understand what we can do, and we defined the critical opening length, which is the distance between the number 1 and number 2 nodes. By that, we can find out what is the effective web opening area. So all the formulae now are coming as a function of the effective web opening area, rather than talking about the exact shape of the web opening. We've run hundreds of thousands of optimization analysis. Just to give you an idea, one of the latest papers, my PhD student, he ran 150,000 models to get one kind of behavior on that particular beam. And we came up with a new kind of shape. We call it elliptically based because it looks like an ellipse, a vertical ellipse, but it's not an ellipse. It's made by 2 semicircles and 4 lines at an angle. And the beauty about that web opening shape is that, first of all, the position of the plastic hinges is always at the corner, so we'll know what it is. But also, we are bringing the plastic hinges away from the top and the bottom fiber of the steel beam. So we'll put them closer to the neutral axis, meaning that lower stresses. Looking more at the structural performance of these beams, we can have now more web openings closely spaced without compromising the web host capacity, so the steel which is between the 2 openings, this one. And in terms of manufacturability, it reduces the cost around 30% by the way that we cut the beam and then we re-weld it. So that's quite a sustainable design. So now let's talk about how we can put that design into the seismic-resistant design of connections, of steel connections. So I will present 4 case studies. I will go quite briefly, especially after the second one. So we started with a welded connection. And I must say that these are standard connections. So these are not seismic-resistant connections. So they're not made by using Eurobot 8, but they're made by using Eurobot 3. So we're talking about rehabilitation. So we always obviously validate our models to show this information to a computational civil engineering conference. So shell elements used everywhere. We always use the SAC protocol from FEMA 350, 32 cycles to understand the hysteretic performance of these connections. And we always play with 3 different parameters. So web opening shape, web opening end distance from the face of the column, and web opening size. So these are the 3 key parameters that we did for all the analysis. And from a quick glance at the hysteretic performance, we can see that the overall hysteresis look the same for pretty much different analysis. But the moment capacity is changing as well as the rotational capacity is changing, and a little bit the steel degradation. If we look at 2 extremes, we see, for instance, the C1400 is with a small web opening, is number 1 web opening, at 400 millimeters distance from the face of the column, and that gives us quite a high moment capacity, a lower ductility. But if we look at the A3, which is the circular web openings, 3 is the biggest ones at 200 millimeters from the face of the column, so quite an opening which is very close to the support. Then we have a decrease of the moment capacity, but an increase of the ductility. Just not to bother too much with that, the main figure that we got from all the analysis is the 50-30. So 50% reduction in the moment capacity will give us a 30% increase in the ductility. So what we actually want. The critical opening length plays a significant role in the steel degradation. So different higher web opening length will give us a higher steel degradation. When we look at the effect of the web opening size, you can see easily from this comparison that the large web openings, they fully form the plastic hinges in these 4 locations. And the stresses in the shear panel zone were reduced significantly. So from these green, yellowish stresses, we get these like blue type of stresses, so much lower ones. So that's exactly what we wanted to achieve, okay? to move the stress, to mobilize the stress away from the connection. Now, the effect of the web opening area on the ductility is quite an interesting one, because we found out that the web opening area effect is not decisive, but what it is the effective web opening. So before I talked about the effective web opening area for every shape, that is what we need to look at, and not the full web opening area. You can see like two different ones, they give the same ones, they give a different rotational capacity, and two different ones, they give the same rotational capacity. So it's really, really irrelevant. Looking at the big picture again, we can see that all the results, they are giving us a better rotational capacity in comparison, and the moment capacity in comparison to the solid beam, so the connection with the solid beam. So looking at the big picture, parameter D, which is the size of the web opening, the bigger the better. Parameter S, which is the end distance, the smaller the better. And with this way, we can control the so-called ventile mechanism, so the shear mechanism, and we can find what is the optimum design. Now, a note here, we're talking about shear plastic hinges, where the RBS connections are talking about moment plastic hinges. But it's kind of ironic, because we're talking about something which is happening close to the support of the beam. So you can better control it with the shear plastic hinge around a moment. But I'm talking about moment because they cut the flanges. So moving to the second example, these are the Northridge connections, in fact. So again, I'm going to skip these slides. We did a validation study. We also ran the monotonic as well as the hysteresis, the hysteretic performance, just to see if there are any differences. Similar type of parameters that we played with. And again, critical opening length plays a significant role in the steel degradation. So we can control what's happening. If you see this example, we have the same elliptically based web opening. Once is located quite near the face of the column, on the other side, so far away. From that case, which is far away, there are still a lot of stresses in the shear panel zone, where here we managed to dissipate the stresses. Now, looking at the comparison between the monotonic and the cyclic, we can say easily that the monotonic is overestimating the results, so higher moment capacities as opposed to the cyclic, which means that never trust monotonic analysis when you do this kind of connections, always cyclic. Again, using the biggest web openings, closely spaced to the face of the column, you will end up getting much lower shear panel deformation, better design, quite effectively. And again, the comparison, if we look at the panel zone deflection, so the connection with the solid beam gave us 20 millimeters deflection, with all the others it gave us lower values. And comparing the monotonic with the cyclic, in all cases we get an overestimation of the monotonic. There is an average of 1.78 and a median of 1.95 when we compare our results. The big picture is again the same. The bigger the diameter, the smaller the end distance, they give us better controllability and better ventile mechanism that we achieve. So we dissipate the energies, we move the energy, the stresses of the energy from the shear panel zone to somewhere in the beam. We also did bolted connections. Now we've had some solid models, and these were quite meticulously done. So all the contact elements, everything was modeled very accurately. I must say that these kind of models, in order to run the full 32 cycles from the SAC protocol, each one of them on a high performance computer took around a week. It's very, very time expensive. Now we played with circular openings only and started having introducing full perforated beams. So one opening, two openings, which didn't really do any kind of difference with that one, and the fully perforated beams to see what's the difference. The main idea is here that once you put the fully perforated beam, you are further reducing the capacity, the moment capacity, by 10–15%, which is quite negative. And we looked at more carefully to see where is this coming from, and it was coming from from the lateral torsion buckling. So we found out that the connections with long, thin thread perforated beams with large web openings closely spaced, they did fail by lateral torsion buckling. In order to better design those ones, what we did is that we moved the first opening closer to the face of the column, like the previous design, and then we continued later on with a fully perforated beam. So if you want to think about it like a fuse design, those that work in seismic, a fuse design kind of thing, where you can even have a different piece of beam there, you can remove it after it's been stressed a lot in the aftermath of the earthquake, and you can pre-stress the whole structure, remove that piece and replace it. So that, in fact, increased back the capacity, the moment capacity, and we had an ideal design. So we can't finish that without saying what we did for the composite, obviously. So we wanted to investigate what is the contribution of the concrete in all that, because we're always talking about just bare steel connections. And we, again, got one from the literature, one experimental work, and we used solid elements. We modeled, again, everything, including the wire mesh, the shear studs, every kind of thing was modeled very accurately, and we used three different material constitutive laws, one for the beam and columns, another one for the concrete, and another one for the stiffeners and the studs. We've used exactly the same SAC protocol, and the comparison is quite satisfactory, so everything worked well. And we had to check first whether the position of the cracks and crashes is happening exactly as where it's happening also in the experimental, and I think we managed it quite well to get all the failure to be similar to the one in the experiments. Now we played with two parameters, in fact, just the size of the web opening and the distance from the face of the column, so we didn't have an apple shape, but we did everything for composite and non-composite. So you can see a pair of the results. On the left-hand side is always the bare steel, the non-composite. On the right-hand side is the composite. If we look at the top left and the bottom right, for instance, this one is a typical connection. That one is with a large web opening near the face of the column. You can easily see that all these stresses now have been moved away from the connection or the components of the connection, and it is somewhere in the beam. Now, looking more closely, the comparison between non-composite and composite is quite surprisingly that, in fact, we didn't get as good as results we would expected when we had the concrete on top. Because the concrete restrains the deflection of the steel beam, which means that we don't really get that variable shear, and we don't really get all the stresses here, but some of them they're distributed in the concrete and back to the shear panel zone. So what we propose is just we need to know what is the contribution of concrete in order to design accordingly our connection. So for those particular examples, the contribution of concrete is different to the positive and negative direction, and you can see that the bigger is the web opening, the higher is the contribution of the concrete. So looking at, on the top, looking at the failure modes, on the top we can see the classic connection on the right-hand side, one with a small web opening away from the face of the column. Nothing's different, exactly the same stresses, exactly the same failure mode. But when we move that small web opening closer to the face of the column, we get a different failure mode. Now it's a flange buckling as opposed to a flange rupture. And some stresses are moved away from the shear panel zone. When we have bigger openings, no matter where they have them, but ideally closer to the face of the column, we have a different failure mode, the variable mechanism, the shear mechanism, which definitely works better for us, and we can control it in a better manner. I must say that the main difference between the variable and the flange buckling is that the variable happens in plane. So we don't have any kind of out-of-plane movement, which is ideal. And we derived also a design methodology. This has been already published. You can't see much actually, but we're using Europe 3 and the Green Book of the connections, moment connections, and we also use a part of the Europe 8. So that is like a fully step-by-step methodology how to design these connections and control the variable mechanism, hence control how many stresses will go from the shear panel to the beam. But I will close in a couple of slides the presentation, and the question is why RWS and not RBS? What do they offer these kind of connections? Yeah, part of the sustainability kind of thing, which a lot of engineers don't really consider. So I don't want to say that the RBS are not good. Obviously, they are brilliant connections. Okay, don't get my message wrong. What I'm just saying is that the RBS connections, they have some kind of issues. One of them is that we do 4 different cuts in the flanges. And if these cuts are not symmetrically done, just by 1 millimeter offset one to the other, it's like an imperfection, so you introduce instability issues. Out of plane movement, and then more likely something like what you see on the picture on the right. Another problem is that you're reducing the bearing depth of the slab, where the slab sits, which means that you lose the compositive action between the steel and the metal deck on top and the concrete. Again, a problem that the American courts, they overcome that by saying that you should not consider any composite action in the area of the RBS connection. So for that zone, say 1 meter from the face of the column, there is no composite action. So you put the sisters just after that. And the last one is that we don't feel that these connections are good for retrofitting. Because you can imagine, you go to the building, the existing building, and you start cutting something which on top there is a slab on it. So you cut the flange, and you may have more movements of the slab, which is just sitting on top. It may even deflect locally. Or on the RWS connection, the reduced web section connections, we don't cut anything on the flanges, so we cut the web. It's just one cutting, so it can be perfect. You don't lose the shear connection, the composite action, and it's easy to inspect, and you can accommodate some services. Obviously, if it's not happening to everything, it's going to be only a few services, but even if for that particular office area or room or flat, you can save some space, it's going to be definitely a positive for your client. And all the other problems that come from the use of pressure beams, namely sustainability. So I will sum up the presentation that the most important factors that we're looking at is the critical opening length, the web opening depth, and the end distance. The web opening area is not a decisive factor, but the effective web opening area. The large web openings, they do play a significant role, especially if they are very close to the face of the column. And all the results that we have got, they have a better rotational capacity as opposed to the previous connections. These new elliptically and patented, these elliptically based web openings, they are behaving better than the circular ones because we can better control the plasticity. So we know how to design those particular ones. And we can custom design, we can do bespoke design for that particular structure. So a number of publications came out of this research, and yeah, I wouldn't be able to end that presentation without thanking my team. So this is the students who did that research, in fact. I haven't run any of these models. And all the funders and partners in our research. So that was the end of my presentation. Thank you very much for your attention. I have to say that I haven't presented an experimental result because it's a computational conference. But we've done all the experiments and calibrated all the models. Yes.
You mentioned at various points the word retrofit. And if I understand correctly, the idea of adding a penetration in a method to diminish the damage to the joint would nevertheless reduce the system strength, wouldn't it?
Mm-hmm. It reduces the moment capacity.
Yeah, so if you had an existing building that did not have perforated beams, but you had some concern that your joints were in danger of performing badly in an earthquake, and you were to start instituting these as a retrofit, what level of diminishment in strength do you think you might see?
You can achieve a better performance. Actually, it will be a lower ductility performance that you will achieve, but you can reduce, say, by 5 or 10% the moment capacity. So you're still within the safety factor.
Mm-hmm.
But then in case of an earthquake, there will be some dissipation of stresses from the shear coming into the beam, and more likely you won't have failure of the welding. So for instance, if you have an elliptically based web opening and you put it at a position, at the medium position as I like calling, so not very near the face of the column, but not really far away, it won't work as an RWS. But if you put it around like 300 millimeters, then you can achieve that.
And as a retrofit solution, has it been employed in industry at all? Are you familiar with it?
Yes, actually in the UK we've already used it, although we don't have earthquakes. But we've used it in a couple of tall buildings. We designed for wind, obviously. And we've done some analysis. In fact, I have some slides after that slide with a IDAS, or a thermodynamic analysis on tall frames. And we show that it performs better than classic ones. I must say in the UK they don't use the RBS, because there's no practice for RBS. Like UK engineers, they haven't used it in the past. So the RWS, we're working with ISTRAC-T and the SCI, the codes. So I'm working also on here with 8. So we actually introduced them in the UK, and we applied them. So we haven't seen the results yet, but they're there.
And one final question, sorry. For the retrofit scenario, is it maybe say 1970s, 1980s type era buildings you're concerned about? I was wondering what the generation of buildings is that is where you're seeing these fatigue.
Well, I think it will be around the 1980s kind of buildings that they have these WFP connections that more ideally we want to use. We wouldn't really touch any building with fully welded connections. But if it's like the ones we tested, these ones, there are extended end plate connections, so the classic bolted extended end plate. So for these kind of connections, all the ones we've used in 1980s in the US, these are the ones that we will apply.
I see there is some displacement, like torsion displacement in the images. Is this not affecting the capacity by the stability problem of this beam?
Okay, so you mean the experimental, right?
Yes.
Yeah, in the experimental, the ones that we actually got lateral torsion buckling, if you see, in the ones that we have fully perforated. So those ones that was just one opening, although we had this kind of restrained frame, we didn't get any sort of lateral movement. But once we had this very thin web, large web openings closely spaced, we did get that movement. But that was not associated to the variable which is happening here. It was associated with the beam, actually, with how thin web it was. So if you see, that one is actually this, but if you see that design, which is the design number 2 I have, which is what I like call it fuse design, although this is not a fuse connection, don't get me wrong. But we moved the first web opening closer to the face of the column, and then the rest is fully perforated. That one did not really deflect in an out-of-plane manner. So it goes really straight down. It creates this variable mechanism here, and it dips down. Of course, in experiments, we have all these imperfections because of the way that we apply the load, some eccentricities. You get a little bit of the movement, but nothing significant. In those fully perforated, I must admit that it was moving quite a lot.
Thank you.
In terms of people with damage resistance, if the building gets damaged and you get obviously the best images from it, is there a quick way to go and do repairs?
I wouldn't say that you can do exactly the same replace as you would do if you want to replace a solid beam. So you can stress the hole from a column, and you can remove the beam and replace it. We haven't done much on that. What we have done, one of my business units, but still a developing ongoing project, is to design this beam, as I said, with a fuse mechanism. So here we have first beam, which is around 1.2 meters. We have 2 end plates back bolted. We have allowed for the penetration of the holes where to pass the pre-stressing, and then the rest is just a perforated beam. So in case of an event, you will move these first bits. Obviously only the bolt connection. We're still working on the analysis though, because it's a bit tricky.